Hello, we're going to do the video for topic C in Module 3, Lesson 25A, and we're going to talk about this beautiful word called geometric sequences, and I'm sorry if there's noise in the back. I have to film this during my flex period. And I just want my bamboo tablet to be plugged in right now. Okay, this way. Okay, so on your screen it says Lesson 25A, Geometric Sequences and Exponential Growth and Decay. The new word in here, something's happening. The new word in here is geometric. So geometric means we're going to multiply, that's the key word, by a factor. All of our patterns will have a multiple that is similar, just like we have found in exponentials, and you're going to see how these two are related. So exponential is still one of your vocab words. Growth and decay is also going to be one of your vocab words. And in this video, we're going to focus more on decay. So let's look at the opening exercise. Suppose a ball is dropped from an initial height h of sub naught, h naught, and that each time it rebounds, its new height is 60% of its previous height. We've all done this before. We've taken a ball, it's bounced, it bounced up, it bounced back down, it bounced up, and a little bit more, a little bit more, a little bit more, a little bit more, until we have to go pick it up again. We've all done this. Every time it bounces, it only bounces 60% of our height before, so a little bit more than half. So think about a ball, it bouncing, and then 60% of that, 60% of that, 60% of that, so on and so on. Let's calculate our height. Our initial height is 10, sorry. Our initial height is 10 feet. So what is H1, H2, H3? So in this is H naught. H naught or H sub 0 means initial in all of your science classes, et cetera, et cetera. So this is H1, H2, H3. That's how it goes. In your notes, you should draw. We're going to draw this really well, but you should just sketch it right now. So H naught, we're going to start with 10. Now, what is 60% of 10? 60% of 10 is 6. So if we look on our calendar or calendar calculator, 10 times 60%, 0.6 is 6, okay? So our first height is just 6. So what is 60% of that? So we're going to multiply that by 0.60. So 3.6. So our height 2 is 3.6. I think it's feet. Not sure. Yeah, feet. 3.6. And then 60% of that, is 2.16. So height 3 is 2.16. And height 4 is 60% of that times 0.60. 1.296. 1.296. So those are the heights. We start with 10, 6, 3.6, 2.16, 1.296. Suppose the initial height is a feet, so instead of 10. What are the first 4 rebound heights? Well, it's going to be, what did we just do in our calculator? We did 0.6 times 10, and then we did 0.6 of that. So we did, 0.6. 0.6 times 0.6 is 0.36. So 0.36 of the height A. And then we did 0.6 of that, so times 0.6, which is 0.126. 0.126 of the height. Oh, these numbers are similar. And then we did 0.6 of that, so times 0.6. So then we did 0.1296 of the original height. What we're going to do is we start with numbers and we're slowly going to replace them with variables so that we can have a general formula for this. So part C, how is each term in the sequence related to the one that came before it? Well, what we did was we multiplied the previous height by 0.6. Because 0.6 is 60%. It's another way to write 60%. Okay, D. Suppose the initial height is A. Good, we did that. And that after each rebound, rather than being 60% of the previous height, is R times the previous height, where R is going to be between 0 and 1. So instead of 60%, we're going to replace it with the letter R so that we can plug in any percent. What are the first four rebound heights? What is the nth rebound height? So here's where we come into more notation, and this is where you do not freak out. We're going to do this one at a time. Height, 1. That's the initial height. And what did we do before? We took 10, our initial height, times 0.6, which was how much it rebounded. But instead of 0.6, we're just going to write R. And then if you notice up here, this is R times A. This is R squared times A. This is R cubed times A. Now it's starting to look like an exponential. So the second height is AR squared. We did 10 times 6 times another 0.6. 10 times 0.6 times another 0.6. H of 3 is 10 times 0.6 times another 0.6 times another 0.6. And H of 4 is equal to AR to the 4th. So for any height, an infinite amount of heights later, say we didn't lose any energy from sound and friction and all that, then H of n would be a R to the n power. Okay. So what kind of sequence is this sequence of rebounds height? Here we go. This is the whole point. This is a geometric sequence. That means they all have this ratio that all the numbers are related by this ratio. Okay, so suppose we define a function f with domain all real numbers so that f of 1 is the first rebound height, f of 2 is the second rebound height, continuing so that f of k is the kth rebound height for the positive integers. What type of function would you expect to be? Basically, they said if this is f1, f2, f3, f4, f9, this is a decay function. The function is decreasing. You took notes one time, and there was an equation like y equals a b to the x. And if b was less than 1, it was a decay function. If b was greater than 1, it was an increasing function. And it's the same case. In our situation, our ratio is 60%, so 0.6, which is less than 1. Let's do some sketching. In your notebook, you should pause and you should just draw a quick sketch, 10 lines up, 10 tick marks the other way, and then we're going to graph this. But we're going to start. It started at 10, and then it went to 6 after the first bounce, and then it went to 3.6. Oh, 3.6. Then it went to 2.16, and it went to 1.29. I don't know if you can hear this, but someone is singing in my flex sphere, which is a very unusual thing. The funny thing is, the person that's singing is also going to watch this video later, so shout out. All right, so here's how the ball is. It's really hard for me to draw. I think if I zoom out, it's a little easier for me to draw. So the ball is going, oh gosh, this is like impossible for me to draw. The ball's bouncing, okay? It's like, pew. Oh gosh, this is not a good, oh my gosh, this is really hard to do with the stylus. Okay, it's bouncing, which is not, let me zoom in. Does the exponential function, here's our initial height, A, here's our ratio, or B, model the height of the bouncing ball? Well, no, the bouncing ball bounces. F of x is a smooth function. So what should it actually look like? Well, what does the function actually model? This actually models a decay function. And it should make a smooth function like this. And the function is The height represents the heights, the maximum heights of the ball as it bounces. So, for bonus points, go take a bouncy ball from your little sibling, bounce it, and then imagine this exponential function. Let me draw it in right now. Orange. So let's take all the heights and draw in, oh, this is not easy to draw in our exponential function. This exponential function represents the initial height, and then it bounces at 60% x. This represents the heights of all the balls. Okay. Summarize. Oh, summarize. Remember, you have I don't know, summary. You have summary, the classwork, and you have the problem set to finish. So get started. Bye.